Hello everybody. Let's do a bit of calculations with buffers and illustrate how a buffer actually works. So let's assume we have a buffer that has a pH of 7.0 and a total concentration or capacity of 200 millimolar. The pKa of the acid is 7.0 and the volume of the buffer is 100 milliliter. So first question is really calculate the amount of acid and base respectively in this buffer. So how many moles of acid and base do we need to make up this buffer? And before we do any calculations, we go back to what we have learned from the Henderson-Hasselbalch equation. And we can write the Henderson-Hasselbalch equation as pH equals pKa minus logarithm of the acid concentration, and abbreviate it like that, divided by the base concentration, and the base I abbreviate like that. And we know that when the pH equals the pKa, we can conclude that the acid and the base concentration are the same, like this. So we know acid and base concentration are the same. And that's a very useful starting point. So obviously we now can use this Henderson-Hasselbalch equation and basically formalize our mathematical thinking here. And I write it down again. pH equals pKa minus the log of the acid over the base concentration. We bring this to this side and we bring the pH to the other side, and we get log of the acid concentration over the base concentration equals pKa minus pH. Now, in order to get rid of the log, we take both sides of the equation 10 to the power of. And on the left-hand side, we've got 10 to the log, because we are log 10, of course, of the acid divided by the base equals 10 to the power of pKa minus pH. Now 10 and log cancels out, and we've got left the acid concentration over the base concentration equals 10 to the power of 7 minus 7, and that of course is 0. That is 10 to the power of 0, and anything to the power of 0 would be 1. So our acid to base concentration equals 1, and that confirms what we said above. We can also say that our total amount of acid and base, and I'll write it like that, acid plus base, should be 200 millimole per liter. That is what our buffer should be. And we can calculate now how many moles of acid and base we have, because we have this concentration, but we only have 100 milliliter. So we can calculate the total concentration I probably should say total amount total amount of acid and base in millimole. We can calculate that. So we would have mole, and for that we have 200 times 10 to the minus 3 mole per liter, and we have 100 times 10 to the minus 3 liter. That's our 100 milliliter. The liter cancels out, the mole is in the right place, so this would give us 20 times 10 to the minus 3 mole, which of course is the same as 20 millimole. So we've got this 20 millimole, that's the total, and we can say the amount of HA plus A minus equals 20 millimole. And we know that the ratio of HA to A equals 1. So we can basically replace HA, or we can say HA equals 1 times A, and we can take that and plug that into this equation. So we've got A plus A equals 20 millimole. And of course we can factor A out, and we have got A equals 10 millimole. And of course HA in this case also would be 10 millimole. So these are our amounts of acid and base that we have given in this buffer. So what can we do with that? Well, we can expand that and we can say, okay, what would happen if we add 1 milliliter of a 1 molar sodium hydroxide solution to the buffer? How will the pH change? Now, of course, before we get started, let's think about it, what this means. We add base to the buffer. So we are adding NaOH to the buffer would make it more basic, or more alkaline. And therefore we would expect that the pH would go up. So that is our expectation, and that certainly helps us to check that our results are correct. Okay, so how do we approach that? So in the first place, we calculate how many mole of sodium hydroxide, or in this case OH minus, do we add? And we can calculate that quite easily. We can say the mole of OH minus. We have mole of OH minus. We have a 1 molar solution, so that is 1 mole per liter. And we add 1 milliliter, so 1 times 10 to the minus 3 liter. Liter cancels out, so that gives us exactly 1 millimole that we add to our buffer. So what happens now with our buffer? we set our starting concentration or starting amount of acid, so HA, that was at the start, we had 10 millimole, and likewise the base, we had 10 millimole. Now, if we add sodium hydroxide to the acid, what would happen is that we have HA plus OH minus, and this would be converted to A minus plus water. So we decrease the amount of HA and we increase the amount of A minus. So if we now write this as plus 1 millimole of OH minus that we add, what we get is we decrease the acid, so we have 10 minus 1 millimole, and that gives us 9 millimole. And instead the base increases because we generate more of the base, so we've got 10 plus 1 millimole, which gives us 11 millimole. And with this information, we can now calculate the pH of the solution, of the buffer solution. pH equals pKa minus log of the new acid concentration divided by the base concentration, the new base concentration, and we can write this as pKa minus log. So what is our new acid concentration? We said we've got now 9 millimole in a volume of 100 plus 1, so 101 milliliter, divided by, we have a new base concentration, that is 11 millimole, and the same volume, 101 milliliter. And in fact, we don't really need to worry about the volume because it cancels out. We also don't need to worry about the millimoles. So we've got pH equals pKa minus log 9 over 11. And if we put that into a calculator, we could get a pH of 7.09. So compared to previously, our buffer solution without the hydroxide ions, we had 7. Now we have a slight increase to 7.09. So that is how the buffer actually works with the hydroxide ion. Now let's compare that to what would happen actually if we just added the sodium hydroxide to an unbuffered solution of, let's say, 7. So what would be the pH if 1 milliliter of this 1 molar sodium hydroxide solution was added to plain water, unbuffered water? And we can, of course, calculate that. So we add, what we do is we add 1 millimole of OH minus. That was the 1 millimole that we've calculated up here. Here. That still stays. 200 milliliter of water, plain water, which should have a pH of 7. And that gives us, of course, a concentration. So we can calculate the concentration in molar. So we have 1 times 10 to the minus 3 mole of the sodium hydroxide divided by 101 times 10 to the minus 3 liter. That's our 101 milliliter because we add them together. And we can calculate that. That would give us roughly 9 times 10 to the minus 3, 9.9, I should say, 9.9 times 10 to the minus 3 molar. Now we can use this now and calculate the pOH, because we've got OH. We can't directly calculate the pH. We can calculate the pOH. The pOH is nothing else but negative logarithm of the OH minus concentration. And that is negative log of 9.9 times 10 to the minus 3. And we remember it always has to be in molar. And when we calculate that, we get a pH of pOH of around 2. So the pOH equals 2, roughly 2. And we can convert the pOH into a pH because we know that pH plus pOH equals 14 in water. So we can figure out the pH. pH equals 14 minus pOH. So for the pH, we get 14 minus 2 equals 12, roughly 12. So this means actually in a solution where there's no buffer, if we just have plain water, we add the sodium hydroxide, we get a pH of 12. Whereas if we've got a buffered solution, we only change the pH marginally from 7 to 7.09. And that is what a buffer actually does. That is the beauty of the buffer. The buffer makes sure that any changes of the pH are really, really moderate and buffered. Whereas if we don't have a buffer, we would have a massive change in pH, and the same calculation and the same principle also applies to any kind of buffer, and even if we use an acid instead of a base. So I hope this makes sense, and thank you very much for watching.